Last time we discussed Boolean functions. That is, functions from that take tuples of binary values and return binary values. We have considered some examples of these functions, but now let us consider one more. It is a well-known function which is called the majority function. The majority function. It is quite interesting for us. So it is a function of 3 arguments. That means that the number of possible arguments for this function is what? How many possible inputs are there for this function? Clearly, we have 8 possible inputs. Hence, in the table of values for this function, we should make a provision for 8 rows. And this majority function takes the value which a majority of its arguments take. So what is the most common value here when we have 3 zeros? What is the most common value if we have 3 zeros? Which value has majority? Isn't it that clear? Okay, it is 0. And when we have exactly one unity among 2 zeros, then clearly the most common value is 0. If we have 2 unities and 1 zero, then unities form a majority. And clearly, if we have 3 unities, unity is the majority value. Okay, it is quite an interesting function, but nevertheless, okay. Should we consider some more interesting functions? Let us do so. Let us do so. Say, let us take this function which is known as Schaeffer's stroke. Schaeffer's stroke. So A stroke B, which is known as Schaeffer's stroke. It is just the negation of conjunction of A and B. So if we take conjunction for Y and Z, there would be 0, 1, 1, 1. But if we want to negate it, we shall obtain just 1, 0, 0. And another interesting function for us for today is just XOR. Exclusive or simply put, it is the sum of its arguments modulo 2. 0 plus 0 modulo 2 is 0, 0 plus 1 and 1 plus 0 is still 1, and 1 plus 1 is 2 or 0 modulo 2. Interesting. Interesting. I hope. Our last question last time was, what does it mean that one can express one function in terms of another one? So we may clearly observe that, say, X plus X is always, what is X plus X? Look here at the table. What is X plus X? Ladies and gentlemen, are you present? Don't you know what is X plus X? Can you see the whiteboard? Show me you are present with both your mind and body. So what is X plus X? Isn't it that hard to tell? It is not that good to use this chat because it's technically hard for me to have a look. So of course, but nevertheless, it is of course 0. So it is always 0. Aha. Okay. But what if I say consider X plus not X? What is it? It is always 1. X implication Y. Here our table lacks this function, but nevertheless we are well aware that it is not X or Y. What do we consider our Schaeffer's stroke? What is X stroke X? What is it? Again, look at the table, please. What is it? X stroke X. Assume that our arguments are identical. Please tell me. What is it? 0 stroke 0 is 1. 1 stroke 1 is 0. So what is the conclusion here? It is not X. It is just this function. But if we have obtained negation, we can easily obtain conjunction as well. How can one obtain conjunction? Provided one has just this Schaeffer's stroke at his disposal. How can we obtain conjunction? Do you have any idea? If Schaeffer's stroke is not conjunction, so what is conjunction? Conjunction is just not Schaeffer's stroke. But easily for every X, not X is just X stroke X. So you can substitute. You can substitute X stroke Y to this expression for X. So X and Y is just X stroke Y stroke X stroke Y. Interesting. And moreover, we know that disjunction, according to De Morgan's law, can be obtained this way by negating the conjunction of two negations. But as both the negation and conjunction can be expressed in terms of Schaeffer's stroke, it is possible that it is clear that there exists some expression which depends on X and Y solely and is constructed with Schaeffer's stroke exclusively. So, intuitively we see that these three very common functions, negation, conjunction, and disjunction, are all expressible in terms of just Schaeffer's stroke. Interesting. But nevertheless, what does it mean that one function is expressible in terms of another one? One can say that it is possible to construct an expression, some term, some word or whatever, some algebraical term, whose value always equals the value of our function. But can we make these things clearer? In such a way that it would be possible to freely manipulate these expressions, to say substitute one for another one. Okay, there is a better way to do these things, not with expressions, but with so-called Boolean circuits. A Boolean circuit is a simple program for computing Boolean functions. So let us define it. First, we shall go informally. So let f be some base, or let's call it p. P be some set of Boolean functions. So assume we have some set of Boolean functions. It is a set of Boolean functions. You know, every Boolean function has some number of arguments. Assume that we have specified the number of arguments for each such function. So the first function takes k1 arguments, the last function takes kn many arguments. So what is it? It is the number of arguments. So here in this upper index, we have the number of arguments of our function. Like, say, conjunction has 2 arguments, Schaeffer's stroke has 2 arguments, negation has 1 argument, and our majority function in this version, in principle, you can generalize it to more arguments. And this version of majority function has 3 arguments. So assume that some set of Boolean functions is fixed. Our next point is to specify some temporary variables. We can employ temporary variables. What are they? They are some discernible objects numbered with natural numbers. So it is T1, T2, T3, T4. They are all distinct. This is the only thing we need from them. Okay. We have some input variables. Which are distinct from our temporary variables. They may be called x1, x3, and so on, or like x, y, z, and so on. They are distinct from our t's, from our temporary variables. Okay? What is a Boolean circuit? A Boolean circuit, or for short just a circuit, over P, is a sequence of the so-called assignments. You can treat them much like you do with assignments in your favorite programming language. or formally they are just pairs of a temporary variable and some right hand side. Let us see what this right hand side may be. Let us see an example first of all. Okay, T1 is assigned to be X, T2 is assigned to be Y, T3 is assigned to be, I would like to negate X, but for formal reasons, I prefer to apply negation to T1. And then as T4 to T4, I'll assign the disjunction of T3 and T2. Okay, that's it. In the right hand sides, I have what? I have either an input variable, or it is also possible to have our temporary variable here. It is not necessary, but it is convenient. And the most interesting case, it is possible to have an application of our function that takes k arguments to some previously defined temporary variables, where f is a function from our base set, and it is important that all these variables are already defined. So what does it mean? That means that this is possible. So these are possible values for the right hand side. The right hand side of an assignment Tj takes value Rj. So, and here we require that every variable we use is already defined as something which has an early occurrence in the left hand side. So, and here we also require that all this I1, I2, and so on must be less than j. Is this idea clear? So, it is a program. What does it compute? What does this program compute? Which function? First of all, every line, every row of this function naturally corresponds to a function of inputs. But what does this program, this circuit, compute as a whole? Do you have any idea? Which function does it compute? Look, let us focus on the last line. So what is T4? T4 is like T3 disjunction T2. But what is T3? T3 is just not T1, but T1 is just X and T2 is Y. So what is it? The value of T4, if we define it naturally, will equal what? Ladies and gentlemen, please tell me, please show me that you are present. Any idea? Which function is computed here? Is it clear? Please let me know whether it is understandable what I'm talking about. Yeah. Okay. Not X or Y. I will continue, but if you do not want to partake, it is almost useless. So it is X to Y, it is an implication. So every line of this circuit. So what is a Boolean circuit? So a circuit over P is a finite, it is important, it is a finite sequence of such assignments like T1 is assigned to be R1, T2 is assigned to be R2, and so on. And the last assignment is something like that, where every right-hand side satisfies this restriction. It is either an input variable or an early defined temporary variable or a function application to some early defined variables. Moreover, we can define the size of this circuit. The size of this circuit is, by definition, that is M. So the size is just the number of assignments here. It is quite natural to map every circuit to a Boolean function. In fact, you can map a circuit of size M to a sequence of M functions. But even if you take just one function, it would be interesting. So let us make an observation. Observe that each prefix, what is a prefix? A prefix is of a finite sequence is its initial segment, the piece that starts at the beginning point of our circuit, but not necessarily including all the and including all the assignments up to one of them. Say up to this one. A prefix of size j. So observe that every prefix, each prefix of size j is indeed a circuit itself. So if we restrict ourselves to some prefix, we will obtain just a circuit. For example, here we may take this prefix and this one and this one, and every prefix and every circuit computes some function. Let us define it recursively. So what is our goal here? What is our goal here? We want to map each circuit over p to a Boolean function. In order to do so, let us fix the list of inputs. I want to make this list finite. So assume that we have n inputs. So it will be a Boolean circuit over p of some of these inputs x1, xn. And every prefix is still a circuit still over p of the same variables. It is not necessary that each variable is used. We want to map every circuit over p of x1, xn to a Boolean function of how many arguments? Of how many arguments? Is it clear to you? And exactly, we have as many arguments as we have fixed inputs to be. Okay, let us do it. We will do so recursively. What does it mean recursively? We will define this function assuming that we already have a function for all prefixes, for all proper prefixes. Every circuit which is a prefix of what is given to us. So let us look at the last line, at the last assignment of our circuit. Let us look at the last assignment of a circuit C. What can it be? The first case, you know, it is important what our right-hand side is. And the right-hand side is either some input variable or a temporary variable defined earlier, or an application of some basic function to a tuple of early defined temporary variables. So we shall consider these three cases. The first case, so our C is something like that. We have C prime, whatever it be, and our last assignment is just this one. So at the last step, we have just take the value of an input number I. So what will be our function be? So we are mapping circuits to functions. We are mapping circuits to functions. So this function will be called GC. Function that corresponds to our circuit C. So then, in this case, our function GC will do what? It takes n inputs and returns. What should it return? It is obvious. Do you understand this?
A function.
Okay, it is a function, but it must return a Boolean value. Which one? Assume that we have denoted its inputs as x1, x2, xn. So which one it must return? If the last line was like that, tj assign xi. Look here, look at this example. So this prefix returns what? What is the respective function. We have inputs x, y, and what should we return? Just x. Isn't it clear?
Okay, thank you.
Is it clear now?
Yes.
So in fact, we are using xi in two senses here. The first meaning is that xi is a formal object, a variable. But on the other hand, xi is just a Boolean value, the input number I. Is this idea clear?
Yes.
Okay. The second case is when our right-hand side calls some previously defined temporary variable. So the last assignment, so we had something in C prime, some prefix, and the last assignment was like that, where I is, of course, less than j. So here, by definition, we must have t1 and so on, tj minus 1. And what should we do? Here we necessarily have ti defined. Is it clear?
Yes.
So in this case, our g c of x returns what? It returns the same, so we can define this function immediately. So it is the function that corresponds to c prime I, to this prefix. We can discern c prime I, the prefix of size I. Is this idea clear?
Yes.
By induction assumption, by induction hypothesis, we have already defined these functions for all the prefixes. Hence, we can take one. And the most important case is as follows. So assume that our last assignment was like that. Tj has taken the value f of t, I1 and so on, tik, where f is a function of k arguments from our base set p, and all these indices are less than j. What should we do? Then our behavior is also quite clear. We shall apply f to what? To the values of functions, corresponding to these prefixes. So we may take a prefix c prime is for every index we have here. Is it clear?
Yes.
It is quite obvious. It is hard, very hard to invent or to imagine anything else here. It is very natural. Do you agree?
Yes.
This equation finishes our formal definition, but in order to really grasp it, let us consider a pair of examples. Okay, a circuit C over the set consisting of negation, disjunction, and conjunction of two inputs, say x1 and x2. Our circuit will be as follows. First, T1 is assigned to be our first input. Of course, we can it is clear that we could use our input variables immediately without firstly assigning their values to temporary ones. But this would make our definition a little bit more complicated. We don't like that. So T3 is just not T1. T4 is not T2. T5 is T1 conjunction T4. T6 is T3 and T1. And T7 is T5 disjunction T6. So we want to find the function which each line of this circuit computes. Okay. So what is the respective function? For each prefix we define it, hence we will obtain it for the whole circuit. Which function do we have here for the first line? It is the projector function that maps a pair x1, x2 into what?
x1.
Look here. x1, exactly. It is a projector that maps a pair to its first coordinate. What about the second line? What is it?
To x2.
2x2. Okay. So this is, say, g1, g2. Let us give some names to these functions. g1, g2. And here we have g3. It is another function of x1 and x2. They are all functions of the same input. And it must be what? It must be negation, yeah? Applied to a function corresponding to the first line, that is to G1. Do you agree?
Oh, yes.
So what is it? Not x1. Yeah? What about G4? What is it? It is not G2 of the same input.
Not x2.
Not x2? Yeah. What about G5? It must be conjunction applied to the values of G1 and G4. But what is G1? X1 and G4, not X2. Do you agree?
Yes.
G6, G3 and
G1.
G1. That is not X1 and
x1.
X1. But okay, that's it, but it is not what we want. Let us correct it. It should be 2 here. So then it will be G3 and X2. And the last one, the function that corresponds to the last line, hence to the whole circuit, is G7, whose value is defined by applying disjunction to the values of X5, of G5 and G6. What is it? Finally, x1 and x2, or and not x2, or not x1 and x2. Can you guess which function it is? Look, when it takes value 1, if and only if x1 is true and x2 is false, or x1 is false and x2 is true. What is it? If we come back to our tables, XOR, of course, exactly. It is our XOR, or just addition modulo 2. It is just x1 plus x2. So we see that the function that corresponds to this circuit is just addition. This program computes addition. So C computes, one can say it this way, computes addition of its arguments, the sum of its arguments, over disjunction, conjunction, and negation. So it expresses plus in terms of conjunction, disjunction, and negation. And this way to express it is well defined. It is quite an easy object for analysis. Look, it is important that at every step, at every assignment, we are applying just one function to some previously defined temporary variables. Is this idea clear?
Yes.
What is the size of C? How many assignments does it have?
7.
7. Okay. But can we construct a circuit that computes addition over the same base but with lesser size? Do you have any idea? In fact, we can. Let us see an example. Consider a circuit D over the same set of base operations of x1 and x2. So now, first of all, we shall compute, as usual, x1 and x2. But then we will compute disjunction of the two, conjunction of the two, of this T1 and T2, and then we assign T5. We assign not T4, not conjunction, to T4, to T5, and then T6 will take T3 and T5. What is it? What is the result? Can we immediately compute the value of our function corresponding to this circuit? What is it? It is a conjunction of what? Of T3. And what is T3?
X1 or X2.
Exactly. It is a conjunction of this disjunction and T5. But T5 is a negation of what?
X1 and X2.
So when is it 1? When is it true, this expression? It is true if and only if at least one of x1 and x2 is true, but they are not both true. So what is it? It's not C but D. What is it?
XOR.
XOR. The same as we had previously. Is this idea clear?
Yes.
Okay. But what is the size of D?
6.
It is 6. So we have used less assignments. So this program is apparently more effective. While they compute the same function, they are semantically equivalent. Is this idea clear?
Yes.
Okay. It is possible to depict our circuits as graphs or some kind of schematics or plots or whatever. Do you know what a digraph, that is directed graph, is? Have you any discourse of graphs?
Not yet, but I think that it's similar to a graph,
Okay,
but
let us
arrows.
consider it. Let us treat it purely intuitively. A graph representation for C and D, for D and C. So, what is a graph representation? First of all, we shall mark our inputs and temporary variables as some points, and then we will connect them in some way. So, first of all, let us start with our inputs. Let us draw an arrow from x1 to t1. So, what is t1? T1 is assigned to be equal to x1. The same is true for t2. And now, considering t3, we will mark this node, this point, with disjunction, the function we have applied here. And then we shall draw these two arrows. Is it clear?
Yes.
Similarly, we can depict T4, this node, or as they say, logical gate, because now it is more and more similar to electric circuits. So T4 is just the conjunction of the same T1 and T2. Look, it is possible to reuse one value many times. This reusing is the most important feature of Boolean circuits, which makes them stronger than other obvious formalisms. Okay. What's next? T5. What is T5?
Negation of T4.
Exactly. T5 is just negating T4. And our last node, T6, may be obtained by taking this conjunction. Is it clear?
Yes.
But look, this works if our functions are symmetric. So like x disjunction y always equals y disjunction x. If had we functions which are not symmetric, this graph representation wouldn't be so nice, because it will be important to specify which input is the first and which one is the second. Is it clear?
Yes.
But nevertheless, for symmetric functions, we are quite happy with what we have. This graph representation is similar to electric circuits. Do you have any idea of real-world electric circuits? Do you know anything about electricity engineering?
Yes, a little.
Okay, so we can represent our Boolean values as whether we have current or we have no current, or in practical terms, upper or lower some predefined level. Is this idea clear?
Yes.
And our elements like disjunction and conjunction can be considered as some devices, some logical gates or vents which map the state of affairs at their inputs to one at their output. For example, this disjunction gate will give us current at its output when, if and only if
T1
disjunction.
and T2.
If and only if it has currents at least one of its inputs. Is it clear?
Yes, yes.
Conjunction will give us current at its output if and only if it will
Both.
have currents at both of them. Negation will negate. If we have current at its input, we will have no current at its output, and vice versa. By the way, from the physical point of view, we see that this negation must have some power source. Do you agree?
Yes.
For if it has no current at its input, it must give some current. How is it possible? We need some power source here, but this power source is, of course, out of consideration in this abstract mathematical scheme. And now let us construct this graph representation for our first circuit C. It starts with the same drill, with mapping inputs to some T1 and T2. But what is going next? T3 is what? Not T1. T4 is not T2. Not T1. Not T2. What's next? What comes next?
T1 and T4.
Mm-hmm. And it is T5. T1 and T4. Okay. And similarly, T6 is just this one. Do you agree?
Yes.
And our last gate is disjunction, which takes signal from both T6 and T5. It is denoted by T7. Look, what is the size of the first circuit? It is 1 plus 1 plus 1 plus 1 plus 1. So it is, we see that it is 6. But here we have clearly 7. The size roughly estimates the number of our logical elements, of our gates. Is it clear? It is
Yes.
like space in computation. So size is roughly equivalent to space, memory space. But what is the right analog to time in this computation formalism? What do you think?
The operation.
What?
the operation or the function,
The operation, but what is operation?
the
How many?
function.
Look, it is quite clear that our computations with these circuits are parallel. They are parallelized by definition. Is it clear?
Okay. Yeah.
If we look at our schemes, so what is the analog of time? It is quite clear to comprehend. In fact, every hour gate has some time to establish the correct output given some inputs. It is not immediate. It is not immediate. For example, you can consider not electric by, say, pneumatic model for that, or hydraulic or something like that. Is it clear?
Yes.
There should be some reaction time of every gate. And when will we have, assume that this reaction time is 1 second. When we will have the correct signal here? After how many seconds? After putting correct signals corresponding to our output, to our inputs here. When will we have the correct output here? After how many seconds? So after 1 second, signal propagates here to these nodes. Is it clear?
Yes.
How many seconds we need for this one? The reaction time of this one plus this one, it is 2. Here,
2.
what about this one? Clearly it is 3. The reaction time of T4 plus 1 second for T5 to react. Do you agree?
Yes.
And it is somewhat more complicated for T6. Look, the first argument will give us the correct value after 2 seconds. But for the second one, it must wait for 3 seconds. So what will be the time when T6 give us the correct answer? Will it be 3, that is 2 plus 1, or 4, that is 3 plus 1?
4.
Of course it will be 4. So we need to wait for every input to give us the correct answer. Okay? So after 4 seconds, we can take the correct answer from this gate. And what about this one? 1, 1, it is more symmetric, it is easier to consider. 2, 2. What about this one? The first argument will establish the correct value after 2 seconds, and the second one after 1 second.
3.
3, here 3, and here 4. In terms of graphs, this is just the length, this number is just the length of the longest path from an input to this node. Is this idea clear?
Yes.
So it is just the length of the longest path from an input, whatever, we should take maximum, to the output. And this value is called depth. This value is called the depth of our node, and in particular, the depth of our circuit. The depth is defined recursively. If we come back to our formalism with these assignments without graphs, we can define depth recursively. Let us do so. One can define depth recursively. Depth is the maximum distance from an input to this node. So we will have our three familiar cases. When our node is immediately an input, what will the depth be? Our last node, we're interested in this one. It is an input. What is the depth? We can put it either 1 or 0. According to this sketch, we can take it to be 1. Is it clear?
Oh, yes.
Some initial value, let it be 1. If you were using some previous value, we can just add 1. So it will be the depth of the node we are taking here plus 1. And the most important equation is as follows. So the depth of this node, where we have f applied to some previously defined values. What is it? The depth of this circuit will be 1 plus maximum of depths of C prime I1 and so on. Is this idea clear?
Yes.
Okay. So let us compute it here. Here we have variable. The depth is 1.
1.
According to definition. Here
1.
1. 1 plus maximum depth of arguments. But here we have one argument at depth 1. So here we have 2. Similarly here, T5, T1 and T4. So we need 1 plus maximum of depths of T1, which is 1, and T4, which is 2. So the result will be 3. Similarly here, and here we will have, of course, 4. Is it clear?
Yes.
Exactly as we have intuitively. And for D, x1, x2 are at depth 1. T3 is at depth
2.
T4,
2 also.
2. T5, not T4. T6,
4.
you should take, you should add 1 to the maximal value of depths of T3, which is 2, and T5, which is 3. So it will be 4.
4.
Okay. So the depths of these circuits appears to be equal. They are of the same time efficiency it takes 4 seconds for both circuits for the signal to propagate from inputs to the outputs. It requires 4 seconds, 4 units at both in both these circuits. But nevertheless, in terms of size, that is space, C is less effective. Its size is greater. Is it clear?
Yes.
So basically, we have 2 efficiency metrics for programs of our language, for our circuits. One is size and another one is depth. Depth is similar to time, size is similar to space. Of course, optimizing circuits, finding optimal circuits is quite a large topic. In general, it is out of the scope of our course. Is it clear?
Yes.
Okay. What should we do? Have not much time, so I want to skip summation of multi-digit binary numbers. It is interesting, but in general it is out of the scope. Okay. So now we have some means of expressing one function via other functions. Every circuit over this set expresses the function it corresponds to in terms of these basic functions. Okay, and this motivates the following definition. What is the closure or functional closure of a set of Boolean functions? So let Q be a set of Boolean functions. Let Q be a set of Boolean functions. Then the closure of Q, which is denoted this way, Q in square brackets, is defined as a set of all Boolean functions for which there exists a circuit it is a circuit over Q, a circuit where we are using just functions from Q, such that F equals the function that is computed by our circuit. Is it clear?
Yes.
By the way, let us define one new symbol, this T. This T will stand for the set of all Boolean functions. It is the union of the sets of functions of n arguments, where n runs over non-negative naturals. The set of all Boolean functions, hence here we have all such Boolean functions which can be computed with a circuit over Q. Is it clear?
Yes.
Look, earlier we have computed addition with 2 circuits, C and D. And both these circuits were circuits over disjunction conjunction and negation. Is this idea clear?
Yes.
That means that we have proved that addition is expressible in these terms over negation, disjunction, and conjunction. It is not convenient to reproduce both pairs of brackets, square brackets and curly brackets. So we shall denote it this way. So we shall write down just square brackets and we have a finite set. This will stand for the closure of this finite set of Boolean functions. Hence, it belongs to just this closure. Is it clear?
Yes.
But can we can we compute, say, disjunction over negation and conjunction? Do we have a circuit over just negation and conjunction that computes disjunction? Can we compute disjunction? So we have two arguments. T1 is x1, T2 is x2. What's next? T3 is not T1, T4, not T2, yeah?
Yes.
T5, we have conjunction.
T3 and T4.
And T6, not T5. So effectively we have computed not x1 and not x2. But this is exactly x1 or x2. Do you agree?
Yes.
So what do we have? In fact, we have proved that disjunction belongs to this set, to the closure of this set. Similarly, conjunction belongs to this closure. Why is it so? Because you know x and y equals not x or not y, and you can easily transform this expression into a circuit. Is it clear?
Yes.
Similarly, implication belongs to the closure of not and disjunction, because implication of x and y is just not x or y. But can we express implication via negation and conjunction, not disjunction?
Sorry, could you repeat?
Can we express implication in terms of negation and conjunction? Not disjunction, but conjunction.
Yes.
How can we do so?
We can
Of course,
express...
there is an immediate argument. X implies y is just not x. What is not x? X and not y. Yeah?
Yes.
But otherwise, we can prove it this way. Ha! We know that conjunction may be computed from negation and disjunction. And disjunction can be computed from negation and conjunction. That means that you can you can somehow replace disjunction here in this circuit with a conjunction. Is this idea clear?
Yes, yes, yes.
It is very important. This intuition is clear. But our next goal is to make this intuition precise. In order to do so, we need some formalities. We are almost out of time, but nevertheless, I think that we have about 5 minutes. Let us do some more observations. We have defined that T stands for the set of all Boolean functions. But what is the closure of T? What is the closure of T? Which functions we can obtain by using all functions?
Every function.
Every function. But why? It is clear that any function we obtain this way is a Boolean function. But why T is included into its closure? Why is it? Is it true that we can obtain every function y itself? Of course we can. But how? It's quite easy to do so. First of all, let us initialize T1, Tn to our inputs, and our last assignment will express f y itself. Is it clear?
Yes, yes.
So this circuit over f and hence over t computes f. So every function is computable over itself. Moreover, we can prove our first general fact here. For every set Q, Q is included into its closure. Do you agree?
Yes.
The argument is exactly same. Every function from Q can be computed via this circuit, and it is a circuit over Q, given f belongs to Q. Agreed?
Yes.
Another lemma. Assume that P contains Q. Is it true that the closure of Q is included into the closure of P?
Yes.
Why is it so? What is the proof? Look, we want to prove that every function for which we have a circuit over Q has a circuit over P. But every circuit, given this inclusion, every circuit over Q is a circuit over P. Is it clear?
Yep.
Interesting. So far, we have two easy observations about closures. So closure of T, the closure of T is just T itself. But what is the closure of the empty set? What do you think? What if we have no specific function? Can we compute anything?
No.
Do we have does there exist a circuit over nothing? In fact, it does. Consider this circuit. T1 assign x37. What is it?
Oh, yeah, it does.
This is a circuit over what? Over the empty set of functions of which set of variables? Whatever, in fact, just including x37. Is it clear?
Yes.
And it computes a function. Which one? The function that maps its 100 arguments into to which one? To the argument number 37. Do you agree?
Yes.
Such functions are called projectors or projections. This function is a projector of 37 from 100. So a projector. By definition, we have that a projector from n, i's projector from n, is a function of n Boolean values such that it always returns its i's argument. Is this idea clear?
Yes.
Let us define the set of all projectors. I will denote it with this bottom symbol. It is to be read as bottom. By the way, you can read this as top. You can read this one as not as T but as top. And here we have bottom symbol. What it is? What is it? It is a set of all projectors, all functions which are projectors, where n runs positive naturals and I is less or equal than n. Is this idea clear?
Yes.
Look, we see that every projector is computable with a circuit over nothing, over empty set. We see that this set of projectors is included into the closure of the empty set. Is it clear?
Yes.
But can we compute anything except projectors? So this set is included into the closure of the empty set. But is it true? Is it true that with circuits over nothing, we can compute only projectors?
Yes.
In fact, it is. In fact, it is. It is true. But how can we prove it? In fact, we need some way to consider all possible circuits over nothing. And then we are going to prove that every such circuit computes a projector. This requires induction over the definition of circuits. But we shall obtain this result from more general things. And these more general things will be the topic, the first topic of our next lecture. In fact, we have the following conjecture so far, that if you take the closure of a closure, then you will obtain just single closure. So closing something 2 times is pointless. It equals just 1 time closure. Is this idea clear?
Yes.
This is the most important fact about these closures. So far, we know these 2 things. And next time, we will try to obtain this one. And as an application, we will answer this question.